for the following, we want to find the open intervals where the function is increasing and decreasing, and if there are any local extrema. We want to find where they are. So the difference between this example and the first and second examples is just the fact of the derivative is not initially given to us already. We're given the main function. We just need to go find the derivative, which is obviously not the hardest of problems here. So the derivative of this function is going to be 9a squared plus 16. Okay, so now we're starting from there. We want it, in order to find the potential critical points, we're going to take that derivative and set it equal to 0. Okay, or this is saying a squared is equal to negative 16 over 9. And looks like right here we got an issue. So if I take the square root of both sides, then making sure I do plus or minus here, I'm getting plus or minus, but I'm taking the square root of a negative. So in sense, it's 4/3 I. Okay. Now, so what we're looking for at this point, the whole reason why we're setting our derivative equal to 0, is we're trying to determine when the graph is going to go from increasing to decreasing or decreasing to increasing. So we're trying to find a point on the graph that allow this to happen. And obviously, if we're graphing the real number system, we can't have imaginary numbers. So what we have just found out that there are no critical points. Okay. Now, as far as the whole intervals of increasing and decreasing, and by the way, since there are no critical points, real quick, there are no local extrema. Because if there's no area on the graph to go from increasing to decreasing, then obviously we can't have a max. And if there's no area on the graph to go from decreasing to increasing, then we have no min. Okay? So they're kind of one and one all going together. But now as far as deciding about the increasing and decreasing, we kind of look at that a little bit. Let's analyze really closely this derivative. Okay? Let's think. If I did it like a sign chart, just imagine here, if I did a sign chart and I just picked a number, let's say, like there's a -2 and let's pick a 4. Go back into your derivative function. If I plug in -2 and square it, it comes out positive. Multiply it by 9 and add 16, it's going to be positive, right? If I plug in 4 squared 16 times 9 and then add in 16 is positive. What I'm saying is that no matter if I plug in a negative number or I plug in a positive number, because of this term right here, it says I'm always having to square it. It's always going to make, no matter what I plug in, positive. And if you multiply it by 9 and add 16, it's always positive. So what we're seeing is the derivative is always positive. So our main function, f of a, is always increasing. Or if you want to say the interval of increasing, you're basically going to say from negative infinity to positive infinity, because it always has to increase. Okay, so let's go on to the next example. For this exact same steps, we want to take this main function. We want to find the critical points and then test the increasing, decreasing, and local maxes and mins. So just like what we did before, let's find the derivative. And to do that, I'm going to write this as 5 minus t to the 1/2 power. Okay, so our derivative, it's going to be the first times the derivative of the second. And then again times the derivative of the base, which is -1. Okay. So all of this is technically the derivative of the second plus the second times the derivative of the first. And then just cleaning it up ever so slightly, so when we go to plug it in our sign chart, we have a little something easier to work with. Let's make this -1/2 t squared times 5 minus t to the -1/2. And then not really a whole lot much we can do, but 2t times 5 minus t to the 1/2. Okay, so first things first, we want to test for our critical points. So when is this derivative equal to 0? Obviously, we're going to move some terms around a little bit. Okay, so this one's a negative term. Why don't we make it positive? So 1/2 t squared times 5 minus t to the -1/2 equals 2t times 5 minus t to the 1/2. Okay. Before we get into a little bit more of the algebra, what I want to do is just really analyze what we're at right now and kind of get the more, I guess if you want to say, obvious critical points. Because let's look. In order for these two functions to be equal, and it's basically one term and one term, can you see, look, let's analyze the values of t. Let's think, if t was 0, if you plug 0 right there and 0 right there, okay, obviously a half times 0 and 0 times that whole parentheses is going to be 0, and 2 times 0 times that parentheses is 0. So when t equals 0, we know for a fact we have a critical point, okay, because you get the balanced equation. Now let's test inside of here. What value of t would make those be 0? Well, obviously 5. Because if that base was 5 minus 5, it's 0, and then 0 times anything would still be 0. Okay, so there's 2. We just have one more critical point. Let's see about getting that one then. Okay, so now that we have our critical points, we're going to use those plus the equation for the derivative to help determine when the graph's going up and when it's going down. So here's my number line with the critical points on it, and we want to test x equals -1. That's to the left of 0. I'm just going to go easy. 1, this is going to be interesting. How about 4.5? And then x equals 6. Okay? So in each case, I'm going to kind of go back up into my derivative. I might clean up my derivative and just see if I can, it might help me if I wrote it kind of in fractions. So how about -t squared over 2 times 5 minus t to the 1/2? And then there was just going to be normal 2t, 5 minus t to the 1/2. Okay, so we need to test positives and negatives. Okay. At -1, if I square -1, it's positive, but it's going to be negative in the top. And if I put -1 down there in the bottom, it looks like it's all going to be positive in the bottom. So this overall fraction, though, will be negative. And then over here, a 2 times the -1 is a negative. I will get a positive right there. So negative times positive is negative. So if I take a negative and add on a negative, I'm obviously going to be negative. Okay? So let's test now with 4, or with, I'm sorry, +1. Okay? At +1, again, I'll get a negative in the top, and I'll get a positive in the bottom. So we're okay there. It'll be an overall of a negative. And then right here, I'll get when I plug in 1, I'll get a positive right there, and a positive right there, so there's a positive. Okay, so it looks like we're going to have to get a little bit more in depth with this as far as getting exact, because a negative times a negative plus a positive is not always a negative. We need actually magnitude. So let's pull out our calculators and let our calculators do a little bit of work for us. You know, sometimes it's nice when you have a graphing calculator because you can just go in and plug in almost like the main function and then just keep changing the t values and it kind of works for you. But when I plug in x equals 1, I get a positive 3.75, so it's definitely going to be positive right here. Okay. And if y'all want me to, I'll go ahead and finish this out for us real quick. Okay, and then what I get when I actually kind of finish this out for us is I get a negative also happening between 4 and 5. Now, something special happened at 6, so I want to take 2 seconds and show you guys what happens when you plug in 6. Let's go back to your function. Let's look real quick at just that base that's being raised to the 1/2 power. It's 5 minus t. So if you plug in 6, what's going to happen? 5 minus 6 is -1, and can you take a square root of -1? Not so much. So what that's telling you is our domain ends right here, that the graph actually does not exist right here. Okay, so when we go to give our intervals of increasing, the intervals of increasing is just from 0 to 4. Our intervals of decreasing are going to be from -infinity up to 0, and then again from 4 to 5. And that's it, because the domain is only from -infinity up to 6. We can't go anything past that. That's mainly because of the function. Okay, so we've got our critical points, we've got our intervals, and now we can test for our local maxes and our local mins. Okay, a local max, let's start here at x equals 0, and let's see. We're going to go from down to up, so that's a min. we're going to go from up to down. So at x equals 4, it's a max. And then obviously, since at 5 there's nothing that we can test is happening over here on this right side right here at all, then that's all we can do. Now, however, because obviously right here at 5 we're at an endpoint because we're at the very end of our domain, we could actually consider that a local min because the graph is going down and it's stopping right there. So we could also consider x equals 5 a min. Okay, we can't consider an absolute max or min, but we can consider it a local one because absolute maxes and mins can't happen at endpoints. Okay, and then if we wanted to talk in the world of absolute maxes and absolute mins, basically kind of knowing this graph, if we got out our graphing calculators and kind of drew this just for a second, what you're going to get is something that looks like this. Here's 0, here's 4, and let's say here's 5. Okay, I'm just going to draw this tentatively. Since the slope is negative, it means it's obviously got to be decreasing to the left of 0. It's got to be increasing from 0 to 4, and then from 4 to 5, it's got to turn and decrease and stop right there. Okay? So that's just tentatively. What I don't know is how high it is, other than just me plugging in values into the actual point itself. But if we want to talk about like absolute maxes and absolute mins, well, because we don't know how high this left side's going to go, we don't know about the absolute max. So we would say no absolute max. As far as the mins, we can say they're low points at x equals 0 and x equals 5. Okay, let's go on to the next example.